Session of the conference, and our first speaker in this session is Ben Torsney, and he's going to talk about multiplicative algorithms for computing optimum designs.
Thank you, and thank you to the organizers for inviting me to this week, and also for an invitation to come earlier, which unfortunately was not possible. It's maybe an honor even to be starting off the very last session of the 4 weeks. I'm trying to resist temptations of thinking of keeping the best wine to last, but that might be more appropriate for some of the last two speakers. Okay, this is joint work with Raul Martin of the University of Castilla-La Mancha, who many of you know. I'm going to cut out the beginning of this material, which means jumping ahead to skip over introduction of optimal design theory, which we've heard a great deal about. Basically, introducing an algorithm and a new use of it, and the results are essentially empirical. So there are several examples. Probably there will not be time to look at them all. So bear with me until we go ahead. Okay. Yeah, it was quicker to. Okay, here is a general problem for which a design problem would be a particular case, and that is to maximize some criterion with respect to a set of variables which need to be weights, negative and sum to 1. Instead of skipping back, I'm going to use some ancient technology, and this is a new kind of word processing package called manu imperfect, or manu imperfecto. Okay, the conditions of optimality for this constrained optimization problem are that derivatives corresponding to positive optimal values at the optimum sum of the p's might be 0, as we know happens often in the optimal design problem. But for those which are non-zero, the partial derivatives of the criterion, and we're assuming differentiability, should be equal to some common value lambda, which in fact is just the expected derivative at that point under viewing the weights as a distribution. And the other derivatives should be smaller than this, or equivalently, directional derivatives, which I call vertex directional derivatives, subtract lambda from the partials, and these f variables should be 0 or negative, according to the weights being positive or 0. This is, of course, the general equivalence theorem. Just look back a couple of slides. To me, this is a nice diagram for illustrating this. Here, representing 3-weight situation, which can such a set of 3 probabilities can be represented in an equilateral triangle. Barbara used it yesterday for another purpose. If all 3 weights are positive, then we're saying the partial derivatives, or the directional derivatives towards the 3 vertices, should be 0, whereas if we run the boundary, one of the boundaries, then 2 of the derivatives, those looking towards E1 and E2 in this picture, should be 0, but the third one has to be negative. So I think it's a nice generalization of standard optimality criteria. So here's the algorithm for finding optimal weights, which has evolved over a number of years. We take current weights, multiply them by a function of current partial or directional derivatives, function which also depends on a free parameter, and then scale these products so that they sum to 1. And the function should be positive, increasing in the first variable x here, and if the second variable is 0, we would like it to be a constant. And here would be 2 examples: d to the power delta if d is positive, or this is meant to be the normal distribution function with argument delta times x. Properties of this algorithm. Crucial one at the bottom is that the weights, the constraints are satisfied. The directional derivative corresponding from, well, here we're defining q here to be the next iterate, to be p r plus 1, given the previous iterate being p. The directional derivative from p to q is positive. Q would be equal to p if delta is equal to 0, and these two together would suggest that the algorithm would be monotonic for small positive delta. This first condition on its own doesn't guarantee monotonicity. We may go too far in traveling from p to q. If we're at the optimum or a local optimum, then there will be no change. So, some key properties. Some results that have been established for this algorithm. If the criterion is a d-optimal one, and we take the function f to be the identity function with argument d, then that is a monotonic iteration. Mike Titchington proved this back in the 70s. If the criterion was a-optimality, then take f to be d to the half, and then you have another monotonic iteration. All of this work really generated from work by Feldman, a paper at Feldman in 1974. He was interested in linear criteria, not in algorithms, but he had a result for the C-optimal, a theorem on C-optimality, which basically said proved this result for that particular case of A-optimality. Moving away from design, if you had data from a mixture of distributions, and the only unknown parameters were the weights, were the mixing weights, then again the identity function with argument d is monotonic. It's an example of an EM algorithm. And some very recent work, Anatoly Zhiglavsky. Well, first of all, I have no major analytical results to report about this. It seems to be difficult to do this. But Anatoly Zhiglavsky and Radoslav Harman have been looking just at the particular case of the identity function and d-optimality, and have managed to prove that the directional derivative looking back the way from the next iterate to the previous one is less than or equal to 0, which is a stronger result than monotonicity given the concavity of the log depth criterion. And I have managed, I think, to generalize that in a very special cases to the general criterion of trace m to the minus t and d to the power delta, but delta equal to 1 over t plus 1. So that's about the limit of results on this. Consolation, although this may sound a bit pompous, I think it was Henry told a story about at some meeting of applied mathematics, someone was running through a set of algorithms and commenting on the properties, and then came to one, the Nelson-Mead algorithm, and the sheet was blank. This was the best, but no one knows why. I would draw any parallels away from there. What I now want to consider, the original, you would imagine that the idea here is to use this to find optimal design weights. But I want to propose a new idea. Well, it's not entirely new. I didn't mention it in the last 3 weeks, but I did mention it at Henry's 60th birthday conference. And in the first instance, it's focusing on determining exact designs where weights don't figure. Supposing we have a finite design interval, A to B, and suppose we want an exact design of m runs. So we need m potentially distinct design points, x1 to xm. We want to choose them optimally. Consider this idea here, that each of the intervals between successive design points is a proportion of the whole interval b minus a. So let's denote these proportions by w1 to m plus 1. We now have one extra variable than x values. But these are variables which need to be non-negative and sum to 1. My proposal is, let's determine the x values through finding optimal w values through using a variation of this algorithm. One major difference from design problems, as I said, most of the design criteria have positive derivatives, and one can therefore use this choice of function. But this will no longer be the case, and is also no longer the case in other examples of this type of problem, like maximum likelihood estimation problems. Under a Bradley-Terry model, the parameters of a simple version of that can be viewed as weights, but the derivatives, some will always be positive, some negative. So clearly, what we're proposing is to use this algorithm and going to make the choice of the normal distribution function and to take the argument to be the vertex directional derivatives for some value delta. And I think we've chosen delta equal to 0.1, and well, f is defined there. So it just remains to look at some examples. There's no need to look at this mathematics, and to comment on some results. First example is to take a model that Henry first looked at, which is an unusual model, a linear and quadratic term, no constant term, and two trigonometric functions. Design interval 0 to 1. I think it's fairly well established that there are the optimal design has a minimal support of 4 points. So here are results for determining exact d-optimal designs for 4, 6, and 8 points. In the case of sticking to 4 points, we hit the optimum fairly precisely after about 68 iterations. If we move to 6, because we no longer can recover the global optimal design, but still we achieve, our criterion is to at least identify when we get the maximum directional derivative below 10 to the minus n. Maybe less satisfactory here is that if you go to n equals 8, which is a multiple of 4, the hope would have been that we would have converged to the global optimum. This hasn't quite happened, although we have found a design with high efficiency. I suspect the problem here is that the endpoint is a support point here, and the method is resistant to replicating that or treating it as having 2 weights. I suspect an alternative approach or a variation of this would be when you know some of the design points, or if you know an endpoint is going to be a design point, then you can fix that, and then you're only looking for the remaining design points. I think if we had done that here and say tried for 6 points, which would have been a multiple of the minimal number 3 these three, we've got 3 design points here, then the algorithm might have performed better. But this, in fact, is the maybe the one black mark here, some graphs, illustrating the performance for other numbers of design points. And there is this resistance to going from 5 to 4 support points in this particular example. Here's the results for a more stable model, polynomial regression degree 5. Again, we hit the optimum in 8 iterations, and here is what was recovered for 7 and 8 points. The designs here, I think, are all symmetric because we start off with the natural starting point is equal values for initial weights. Here, equidistant distances between design points, and that would, if you start out with symmetry, that will be preserved throughout iterations. That was for one design variable problem. Extending it to 2 design variables. Well, here's a quadratic model. Design interval, both variables lying between -1 and 1. One way of thinking here is that we take x1 and divide up the range of values for x1 into subintervals, and then for each x1 value we want to split x2 up into subintervals. So what we're thinking of here is that we want to find a marginal optimal set of w's for x1, and then optimal conditional margins for x2 given x1. So there are several distributions which we want to find, and the algorithm naturally extends to that situation. And because in this simple case the result is well defined, here is the optimal design here, and we, well, 9 of course, is 9 support points are needed but, for that optimal design, but we have found the optimal designs for 6, 7 and 8 points. So it's a 6 parameter model, and that works fairly well. We can move on to models with correlated errors, and then, as others know, there are additional parameters from the covariance parts of the model, and you could be interested in either theta or r or both, and we have explored different choices. So here's one particular example, just a linear model with this quadratic exponential correlation function or covariance function. What is known, as we've heard before, is that we cannot have replicates in this situation because 2 such observations would be highly correlated, but established algorithms that sometimes converge to that. So you need to add in an extra parameter to avoid this. Although, so here are the algorithm can be straightforwardly applied in this situation, and we've tried this for different values of r, as we'll see later on. I think here's a nonlinear model from Fox and Lucas, optimal design that they found. Clearly, the design here is parameter dependent, but we have applied the algorithm in this situation. and we're just recording here the maximum of the information, determinant of the information matrix for choosing different values of R here and different numbers of runs, and recording the number of runs also to achieve this condition, maximum directional derivative below 0.1, 0.01, 0.001. Okay. Well, I think what now we'll do is just jump to the end to show an extension of this. I've gone too far. No, I've gone too far. You can, yeah, this is it here. Here we consider the notion of applying the algorithm to find both support points and optimal weights. And we can invoke Carathéodory's theorem to identify an upper limit on the number of support points. So the idea would be start out considering that you might need a design with the maximum number of support points, and then we want to determine their optimal weights. Well, again, what we want to do here is find two distributions, but the algorithm easily extends to that situation. Now there is the option of choosing different functions. This kind of choice here would be appropriate for the design weights, but we need to go for a function for the w's that allows for negative derivatives. And I think I will just go back to Henry's example. Here's the choices we've made for this algorithm. So the choice that was known to be d-optimal, to be monotonic for d-optimality, and then making this choice for weights. And it works pretty well. Here are the pictures of results achieved through various sequences of the application. And this time we do end up with just 4 support points and not the extra one that was needed when the weights were assumed to be uniform across an initial set of design points. Okay? Yeah.
We have plenty of time for questions, if anyone has a question.
Then how does the algorithm perform when you vary the values of delta?
Well, if delta normally cannot be too large. In fact, if you made delta extremely large, say d to the power 1,000, you will converge to just one-point designs. You're just going too far from where you start and well past the optimal. And what is not clear is, well, one might consider trying to choose the delta parameter optimally in some way, but what you want to avoid is making this function that you're multiplying the weights with, you want to avoid it being them getting too large, or that the set of such values are too extreme. Otherwise, you will be putting some weights to 0 that shouldn't go to 0, and it's really ongoing research to try and figure this out, but it's not a clear answer, and of course it would depend on the problem. I mean, for d-optimality, you get better convergence if you allow the delta to go up to almost 2. There are examples where you can show that simple examples where you wouldn't need numerical methods. So if you take if you take delta equal to 2, you will get an oscillating sequence. For the C-optimal criterion, you will get delta. The same thing would happen for delta equals 1. So the main message is that delta, this free parameter, must be kept within certain limits, but what limits is not clear.
As far as I can tell, you're using the spacings between the design points.
Yeah.
So if you think of the spacings think of this, the empirical CDF, that's
Yeah.
a bit like using the quantile function of the design.
Yeah.
I think, I'd have to work it out. But then to go to higher dimensions, you would need to use some kind of generalized quantile function. I'm just giving you a few words to use. That's all.
Yeah, well, there was a couple of examples of two variable problems. So we used the notion of a marginal distribution for one and a conditional for the other. But yeah, some joint distribution might be more.
The joint quantile function. It's like, I mean, speak to Sandra knows all about these things.
Oh, right, okay. In fact, I had one conclusion. This clearly requires the design interval to be finite. But if you move to nonlinear design problems like binary regression, the design interval does not need to be bounded. However, the solution is transform from design variable x, say, to f of z, where f might be a distribution function, and that in fact would be a very appropriate choice for binary regression. Use the same f as in your model. I close some papers and results on optimal design quote not the design point values, but the probability values, the CDF values. So in effect, that's what we would be trying to find those directly, rather than finding the x values first.
Other questions? Okay, well, let's thank Zen very much.